This is a demonstration of the energy density of nuclear fuels. This does not take into account conversion efficiency, merely the total energy available. We have here a cubic meter of plutonium-238. Next to it, we have a very unfortunate man who is being roasted alive by alpha particles as the plutonium-238 decays. Behind the cube of plutonium-238 and the very unfortunate bloke is a massive cube of coal. It is 109 meters wide, 109 meters tall, and 109 meters deep. That small red cube of plutonium and the large black cube of coal contain the same amount of total energy. It should be noted though that plutonium-238 is the least energy dense of all nuclear fuels. Let's have a look at some of the others to see how energy dense they are and how much coal we need to be equivalent to those fuels. But first, here is the Perth Bell Tower for a size comparison. This iconic West Australian building is 82 meters high, but it is dwarfed by the plutonium-238 coal equivalent cube. This here is a cubic meter of thorium metal. It is currently not used much for energy generation, but will probably be the world's leading supply of green energy by later this century. Moving the amount of rock required to build the Great Pyramid would be cakewalk nowadays, thanks to modern machinery and the energy that powers them, including nuclear fuels indirectly. This right here is a cubic meter of uranium-235. Although uranium metal is a dull grey silver usually, I've shown it here as its ore, pitchblende. You'll just have to imagine that there's uranium metal below the surface of the pitchblende. Uranium-235 is the most common type of nuclear fuel. Uranium-235, however, is just a tiny proportion of all naturally occurring uranium. Although it's only here to give you a sense of scale, this is Perth, Western Australia's most iconic skyscraper, 108 St George's Terrace. It's also known as the Big Sharpie. Our man in white has just somersaulted over a cubic meter of plutonium-239. This stuff is really, really energy dense. For this demonstration, I've gone with the lowest energy density estimate of plutonium-239. That cube of coal equivalent could have been much, much bigger. This here is my interpretation of antimatter. This in particular is a cubic meter of anti-H2O, anti-water. In reality, this stuff would have already reacted with the atmosphere around it and released its energy. A big explosion would have been the result. How big? As big as if this mountain of coal were to explode. From this, I hope you can see that nuclear fuels are really something. All the world's large ships could be nuclear powered, saving diesel fuel for other purposes. Nuclear fuels are also very low carbon fuels, if you're worried about carbon dioxide in the atmosphere. And with China, India and Russia developing molten salt reactors, nuclear power is only going to get better and better.